So last video we talked about this term Q, the specific discharge. And remember that it's the volumetric flux, volume relative to the area through which the flow is passing. And we said that this Q term has dimensions of length per time. I want to ask you a question. Is this Q term the velocity that individual molecules of water are traveling at? So if we were to look at some little snapshot of a porous media, these are some sand grains or gravel grains or something. And there was some flow coming out of this whole area here, Q. Q is not the water velocity. And the reason is that if you're an individual water molecule and you're moving through here, even if there's a certain flow in aggregate, at the pore scale, you've got to go around these grains. And so you're traveling a much longer path, and so you're actually traveling a fair bit faster. And so the mean pore water velocity is related to Q, but it should actually be a fair bit faster. And so to make this a bigger number, we're going to divide it by something. And the thing we're going to divide it by is the effective porosity. So you can imagine if there's in the limit, when the effective porosity is 1, there's no obstructions, then Q just is the mean water velocity. But as the effective porosity gets smaller and smaller, these water molecules have to travel further in the same amount of time, and therefore you're dividing by a smaller number and you're getting a bigger pore fluid velocity here. So that's the intuition for this actual mean pore water velocity. We also want to consider when Darcy's law is even valid. So we talked about Darcy's law. And it's valid not in all circumstances. It's valid actually for slow flow, viscous flow, or laminar flow, or not turbulent flows. So it's not valid in, for example, a river where you've got turbulent flow, it's moving super fast. It is valid here where the flow is pretty small and you're going through this packed porous media. It's not valid in big open pipes, for example, because again, the flow is too fast. And a physical way of describing this particular condition is that it has a low Reynolds number, RE, and that means that the inertial forces are small relative to the viscous forces for this particular water body. So those are the flow conditions, but there's also a spatial condition that we need to consider. And so Darcy's law is valid in these conditions. It's not valid at the scale of an individual pore. So if you were to zoom in microscopically and look at the water molecules in this particular pore, the ones in the middle would be going pretty fast. The ones really close to a grain boundary might be going really slow. You've got this distribution of velocities. And so to get to this overall aggregate behavior, you kind of need to zoom out. And so Darcy's law is subject to the representative elementary volume consideration that we discussed before. So the REV consideration. Or to some macroscopic aggregate behavior. Macroscopic behavior. So just some word of caution about the domains over which you can apply Darcy's law. It needs to be fairly slow flow within a porous media, and you need to be looking at a certain size before it's actually valid here.